Okay, so this is week 3, the first hour of week 3, and in the first hour, we are going to continue talking about data and how to use graphics and visualizations in showing data, which helps us understand the data that we have better. So we already discussed box plots in the last lecture. So today we're going to talk about histogram analysis. Now the histogram shows the distribution of values of a single variable. So we want to see the distribution according to this a variable, which is unit price here, and we want to create, or we usually divide the values into bins. So we say that the values from 40 to 59, from 60 to 79, from 80 to 99, from 100 to 119, from 120 to 139. So these are the bins. And each bin will show the number of or the count of items sold within these prices. Now the choice of bins depends on you, on the researcher, and it's worth to say that that the shape of the histogram will depend on the number of the bins that you choose. So in this case, we have 5 bins, so we'll have this distribution. If we increase or decrease the number of bins, we may have a different shape of a histogram. Generally speaking, histograms tell us a lot more than box plots. Now, according to this example, these two histograms, they show the same box plot representation. So they share the same value for minimum, maximum, Q1, Q3, and median. However, they have a different data distribution. So histogram will show us data distribution better compared to box plots. Another graphical display of data is the quantile plot, and the quantile plot will actually display all data and will highlight the Q1, Q3, and the median of the data. So showing only these values for the data, and will show the unusual occurrences because it will show the data that is below the Q3 and the data above, below the Q1 and above Q3. We also have the QQ plot, or the quantile plot. And in the quantile plot, we're actually comparing between two attributes. In the example here, we're comparing branch 1 and branch 2 in terms of their unit prices. So we're showing a comparison between two branches and how much they sell of each item. Now, according to this data here, we can say that unit prices of items sold in branch 1 are lower than in branch 2. Now, how do we know that? If we go to the Q1 here, you will notice that the Q1 is almost 60, okay, while in branch 2, Q1 is a little bit more than 60. So it is less compared to branch 1. Branch 1 is less than branch 2, or cheaper than branch 2. Now we also have the scattered plot, and the scattered plot will actually show a comparison of between two attributes, unit prices and items sold, and it will show actually how data is distributed. Okay, it will also show outliers, so you can see here that there are some outliers. It will also show if there are clusters of points or a group of points that are together, like here for example you have a cluster of points. So it does show how each of these values plotted into the two different coordinates and the intersection between them in terms of points. Now, scatter plots show correlation, and they can show negative correlation or positive correlation if you can draw a line between them. So if you can say that, if you can see here, you will see that there's a line, or you can draw a line of data, and here you can also draw a line of data. Now since the data here is increasing, so we're actually saying that this is a positive correlation. The more this attribute or this value is increasing, here is also the value is increasing. Now here, since the values are going down, we say that is negatively increasing. The more here the values are increasing, they are decreasing here. And of course, scatter plots can show uncorrelated data, so you cannot make anything here. You cannot see any kind of correlation. They are only scattered around. They're not correlated. You cannot draw a line that is ascending or descending. Here we have like you can think of a horizontal line or a vertical line, but this is not correlation. Now another well, we're going to talk a little bit in depth about the different categorization of data visualization. And data visualization is a thriving kind of science, because data visualization allows us to understand data in a way that you can see and present in front of yourself. And data visualization is actually used in the analysis, or we call it the exploratory data analysis. Now, why data visualization? First of all, it allows us to gain insight. We are able to see information in front of us in forms of graphics. And this actually provides us a qualitative view of large data sets. Now, large data sets filled with numbers and values and attributes are a challenge for us, for the human mind, to understand. We use descriptive statistics for us to further understand it. However, data visualization makes us have an overview assessment of the data, especially if it's a large data set. Also, it allows us to search for patterns, trends, structures, irregularities or outliers, if there are relationships among data. All of these can be discovered through data visualization. It also can help us find interesting regions or let's say groupings of data. It allows us to see correlations between different attributes, and it also provides a visual proof of what does the data mean. So it is easily understood for even non-specialists. Now, we have categories of visualization methods, and we're going to go through some of them with some examples. So we have pixel-oriented visualization techniques, we have geometric projection visualization techniques, icon-based visualization techniques, hierarchical visualization techniques, and also visualizing complex data and regions. So, well, the first one is the geometric projection visualization techniques, and within these we have many methods. But from the name, it actually uses geometry to transform data into geometric forms, into lines, points, 3D or 2D shapes. All of these are considered to be geometric projections. The examples of this kind of visualization techniques include direct visualization, scatter plots, just like we looked at them. We have also landscapes. We're going to look at some of them. We also have projection pursuit techniques, which shows projections of multidimensional data. We also have parallel coordinates. We're also going to see an example of that. So this is an example of a direct data visualization, showing some ribbons with twists on them. So and they showing that is based on vorticity, which means what do you call it, like twisters, the air moving in spirals. So this is not actually representing air, it's representing data, showing data in this form. So this is actually a data visualization technique. This is a scattered plot metrics. We already saw the scattered plot, but this is a scattered plot metric where we're actually each square here is showing a relation between two different attributes. So each one of them is showing some sort of information about two different attributes. So one of them is a scatter plot, but this is a scatter plot matrix because it is displayed in this form. And it is actually showing, if you see, that these pairs here will have actually the same kind of correlation showing. Okay, some of these data are similar, if you notice. So it only shows that not only one scatter plot between two different attributes, actually showing scatter plots from many pairs of attributes. There's also landscapes, and the landscapes actually show the data in a form of a landscape, like a land. You can see that it looks like hills and mountains, and it's pointing here to the meaning of each one of them. And we differentiate between data in terms of color, that shows also in terms of height and depth. All of these are actually showing different attributes of the data. However, this is actually considered to be a 2D spatial representation. So it tries to preserve the characteristics of the data, showing that, for instance, court and FBI should not be with the same height. So it means that there are differences between them. There is also the parallel coordinates. And the parallel coordinates is actually showing, if you notice here, different attributes. So attribute 1, attribute 2, attribute 3, until attribute K. And these attributes, or these coordinates, they are parallel, and they are equidistant, which means that they are equal in distance. So if there is another coordinate here, it should be around here exactly. Now, the axes are scaled to the minimum and maximum range of the corresponding attributes. So here, the length of this line should scale to the minimum and maximum values of this attribute. And every data item for instance, between attribute 1 and attribute 2, it's actually, this line here is showing that this is the value of attribute 1, and this is the corresponding value in attribute 2, and this is the corresponding value in attribute 3, and so forth. So this is an actual parallel coordinates visualization of data, showing how different values of different attributes are corresponding to each other. This is the same kind of visualization, but it's actually using colors, just to distinguish between the different attributes, and it's actually showing for a data set consisting of 3 attributes here. There's also the icon-based visualization techniques, and in this type we're going to mention or discuss or look into 2 methods. So in this type of visualization we use features or icons. Features of icons actually, in order to display data. And we have the Chernoff faces and we have the stick figures. And the typical, the general techniques between the 2, and you'll notice when we see the examples here, is that they use shape encoding, they use color icons, and they also use tile bars. So shape encoding, it means that they use some features within the shape, either the face or the stick figure, as we will see in a minute, to represent certain information. The colors are also used to encode some information. So they show some information using colors. So red will mean this, green will mean that, etc. And the tile bars is actually the using of small icons to represent the relevant feature vectors in document retrieval. So this is actually used with documents. So this is an example of the Chernoff face. These are Chernoff faces, and it is used to display variables on 2-dimensional surfaces. So X will be eyebrow slant. Slant means if they are here, they are straight. Here they are a little bit going down. Here they're going up. So Y will be the eye size, Z will be the nose length, etc. So in this example here, we actually have 10 characteristics. It is showing the head eccentricity. We have the eye size, the eye spacing, which is the space between the eyes. We have the pupil size, the eyebrow slant, as mentioned before, the nose size, the mouth shape, which is different shapes, and we also have the mouth size and the mouth opening. So each one of them will have different values to display the data, and this is a very unusual way of data visualization. These are some of the web resources that you look into, but you just need to know that how the Chernoff faces are use the surfaces of the face to display characteristics of data. The stick figure also have the same idea. However, we use the coordinates, so to display that this is representing the information between income and age. Okay, so however, income and age are represented here, but the 5 stick bodies, these here, they also show other characteristics. So each figure will have the body and 4 limbs. So it will have the body and the hands, the arms and the legs. And for the arms and the legs and the body, we will have angle information and we'll have length information. And this will include or will encode other information from the data. So it's not only about income and age, there is more decoding here within the stick figures. Also, we have hierarchical visualization technique, and in this way we use hierarchical partitioning into subspaces, which means that we divide the data into multiple subspaces. We're going to look at dimensional stacking. There's also worlds within worlds, tree maps, we have cone trees, and we have also info cubes. So the dimensional stacking, it's actually about partitioning of multiple dimensional attributes into a 2D or two-dimensional subspace. And that's why we have to have it stacked, because it is multiple dimensions and we only have 2 dimensions. And in this way, we partition the value of the attribute into ranges, or as mentioned in the histogram, into bins. So we'll have like classes. In this way, let me just show you. It is, first of all, this way is adequate for data with ordinal attributes and low cardinality. Low cardinality meaning that there are no many unique values in them. So this is the best kind of data that works with this kind of dimensional stacking. So this is the dimensional stacking, and it shows, so it's a visualization of oil mining data with longitude and latitude mapped into outer X and Y space. So longitude data and latitude data into XY space. This is a two-dimensional representation that we are used to, X and Y. Now, for each one of the other dimensions that we want to see, we have two sub coordinates in the middle. So here we have sub xy and z, xy, and here is xy, and here is xy, and here is xy. So each one of them is actually representing a 2D x and y axis, inner x and y axis. There's also the worlds within world visualization, and in this case we try to represent the data in a form of a plane. So it allows us to show or to draw worlds of 1 or 2 or 3 dimensional words using different set of axes. So you see that we have here x4, x5, x2, and this is f, and this is x1, x3. So these are multiple dimensions. So it's a multi-dimensional view of the data, and it requires highly specialized software in order to be able to draw them in this way. And examples of these are InVision, and also we have AutoVisual. They allows us to provide this kind of representation of data. There's also tree maps, and tree maps are very common. They're commonly used, and it's known in the data visualization field that tree maps provide very beautiful. The examples here are not actually showing any aesthetic value. It doesn't look nice, but it's known that tree maps provide sometimes beautiful data representation that are sometimes presented as art. So first of all, it's a screen filling method, which means that you will have to fill the whole screen using the tree map to show the data. And it provides hierarchical partitioning of the screen. So you will be dividing the screen into regions, and each region will have an X and Y dimension, and will also have different colors showing different classes. So it's actually, it looks like the stacked partitioning. However, it also uses colors to provide differences, or to provide classes of data. There's also the InfoCube, and the InfoCube is actually a 3D visualization of hierarchical information that is displayed in cubes that are semi-transparent. So if you notice, we have like a big cube and then you go inside, you see another cube, and you go inside and you see another cube. So there are cubes within cubes, and they are showing the data in a way that the outer cube is actually the top level of data, and the subnodes and the lower levels are represented by smaller and smaller cubes as you go on. And it's difficult to view here because the picture is not clear, but it is. You just need to know that it's cubes inside cubes, that this is InfoCube. There's also the 3D con tree. First of all, the 3D con tree will build circles. So we'll have like list of circles, okay? And these circles spiral until the end, or until the top. And then there will be data representation similar to the parallel representation of data. So you will see that there's a point here that is leading to a point here, and there is a point, this point is leading here, and this point is leading here, and so forth until you go up. It's clear here in the green one. It shows these relations between these points. So when you try to show them in a 2D shape, it is hard to actually identify it, but it's much clearer when you show them in 3D shape here. When we have complex data in terms like textual data and social networks data, we use different kind of visualization. Sometimes we use tag clouds, which shows user-generated data, and the important hashtags or the important words will have a bigger size and a different font maybe, or different color, and the ones with the smaller fonts is actually considered to be less important. So textual data in social media is usually represented using these tag clouds. Tag clouds are used also to represent or visualize social network or social media networks.